Yes, the other mistake I made is when I said that you were mostly space, nothing at all. The amount of space is less than what I said. It's only 99.999999999% space. Still, you're pretty well all space. So we left off that you've come down and made it to the solar system, and the number of steps you had to go to get to get that. Um, the Earth then was so hot that life could not have existed for the first half billion years or so. But then when life came, it was pretty boring because it was just like one-celled, which split into two, cloned. So that, and eventually, of course, the cells became larger and larger groups, and eventually became organisms with several cells. But it wasn't until really you had sex that things really took off. And that was about half a billion years ago, the kind of sex that we think of nowadays anyhow. And you get half of your genes from your biological mother and half from your biological father. So you are, as far as your physical makeup is concerned, one half your father, one half your mother. So when people say, well, you're just like your mother, or just like your father, well, half of you physically is exactly like you have the DNA of your mother and your father. And your DNA then is, when you get to multi-celled organisms like yourself, complex life, it's composed of, as I say, cells. You get half your genes from your biological mother, half from your biological father. And your cells have a core. In the core, there's what is called deoxyribonucleic acid, DNA. And that gives you most of your physical characteristics: the color of your hair, color of your eyes, size of your nose, how big it can become, etc. And in that case, how you grow is the DNA is like a ladder with rungs in between it. It's actually composed of 4 different chemicals. But when you grow, the ladder is split down the middle. And it's twisted, so it's called a double helix. And then you get a new left part or a new right part that corresponds to the other side exactly billions and millions of times. Except when it doesn't. For some reason, misfire, perhaps some radiation, a cosmic ray gets through, they don't always match up equally. And because your DNA gives you physical characteristics, that could mean that your physical characteristics will change as well over time. And that if that physical character, the DNA changes, then that is passed on to their offspring. And that process is called mutation. So basically, that's happened in the past several times. So basically, you're a mutant. You're really a mutant. Now animals grow like that, and they take in oxygen from the air and give off carbon dioxide in the process. So plants do the opposite. It's like a symbiotic relationship. They take in carbon dioxide and give off oxygen. A process called photosynthesis, where they take the light and energy from the sun in order for them to grow. Now the life started off, figure, in the ocean, and even without the sunlight through some chemical reactions at the bottom of the oceans. They figure that their life started there because there are some animals there. And it's too deep for sunlight to get through. So there's a different hypothesis as to how life started. But life started in the ocean and came up onto the land. And science does not have an answer to how life started. They have some speculations, they have a hypotheses. You take these chemicals, mix them together, put a little energy in, woof, you get life. But they have not seen it directly, nor have they produced it in a lab. So before they can do that, you can't really call it a true scientific fact. You can say it's a probability that this is what happened, or there's a hypothesis, but not a scientific fact, or not a true theory or a law. So there's another example where science does not have, yet at least, the full answer to how you got here. But there was, as I say, a symbiotic relationship between plants and animals. But one smart-ass plant wasn't satisfied with, like the rest of the plants. He grew higher so he could grab more sunlight and become bigger. Now, when most plants die, they rot and give back the carbon dioxide into the atmosphere. But when the trees died, they just didn't rot for millions of years. They just lay down and were squeezed into coal. So that's where you get your coal from. But because they didn't give back the carbon dioxide when they should have rotted, there was more oxygen in the air at that time. So your animals, which were insects, could have been much larger. Insects breathe through tubes, and some of the oxygen is absorbed in the tube. But if there's more oxygen, the tube can be larger. So centipedes, for instance, could have been the size of a crocodile. But there's been many close calls you've had during the life of the Earth. And often, when you look at the geology of the Earth, the different time periods, there's been some pretty disastrous events. Like often you separate the Triassic, Jurassic, Cambrian, and so on, and looking at where they switch from one to another, there's often a tumultuous period which threatened life. 5 major ones. One of them happened 225 billion years ago in Siberia, where all these trees had fallen down and became coal, had heated up probably from volcanoes and set the coal on fire. At least this is what many scientists think. And that caused so much problems that 90% of the animals in the ocean died, or 90% of the life, rather, and the rest on Earth. 70% in total of all life became extinct. So you're lucky to get through that. Then the dinosaurs ruled the Earth for 160 million years. And the dinosaurs are cold-blooded. So they require warmth or sunlight for them to move around. So at night they're pretty dormant. And you, being a mammal, you have to stay underground, because if you came out in the daytime, you can stay underground because you're warm-blooded. You can operate in the cold or without sunlight. And you would only come out at night then to feed, because if you came out in the daytime, you'd be gobbled up by all the dinosaurs. But 65 million years ago, we had a great event, which wiped out the dinosaurs. Now, during the time of the dinosaurs, there was one large continent called Pangaea, and it split up to the other, and became all the other continents that we see today. I mean, they're still moving around, but still. And if you look at South America and you look at Africa, you can sort of speculate that, yeah, they look like they fit together like pieces in a crossword puzzle, jigsaw puzzle. But until I think 1946, there was no proof. I mean, you could, maybe some people had seen, oh, isn't that odd? But they never really put two and two together. It remained to Wagner. He not only looked and said that, the planets seemed to fit together like the pieces of a jigsaw puzzle. He had got empirical proof for it, rather than just deductive. He got some actual empirical evidence. He looked at the fossils of plants and animals on this side of the Atlantic, and then looked at fossils of plants and animals on the other side of the Atlantic, and found them to be the same species. And they exist in no other place in any of the other planets. Then he looked at the land formations on this side and the land formations on the other side, and he found that they started on one side of the Atlantic and continued on the other. And in particular, a sedimentary rock, which puts different layers down in different places and different thicknesses. He found them to places where they matched up totally, indicating there must have been a split right at that point. And the fourth thing he did is looked at the fossils in the northern climates and found that those fossils could only have lived in the south, so that the land must have moved from the south to the north. Now, this was a great discovery. So was he heralded as one of the greatest geologists or scientists? Far from it. The actual opposite. He was vilified. He was made the laughing stock of the scientific and geological communities. They said, in their opinion, the consensus of the scientists said, that's ridiculous. So rather than following the evidence, they discarded the evidence. They didn't even look at it. And science should look at the evidence wherever it leads you. Not rely on merely opinion, even if it's the consensus of the scientific community. In this case, they were totally wrong. It remained until 2 decades later. Now, I'm not sure it was 46, but anyhow, two decades later, for another scientist, to explain how it could happen. The continents ride on plates, and the plates move around on top of the magma. And they split up, and when they hit, they form get all your volcanic activity and earthquakes. And for instance, you get the Himalaya mountains, where India split off from Africa and bashed into the Eurasia and formed the Himalayan mountains. So that theory is called the continental drift theory, and now is accepted. But when Wagner first did it, no. And he went out to the Greenland to try to find more evidence. He helped out some stranded people in the snow, and walked off, and never seen again, not knowing that his theory, and you can call it a theory, because it has evidence to support it, would be vindicated. He would be vindicated. But as I say, 65 million years ago, Jupiter, the most massive planet in the solar system, more massive than all the other planets combined, let down its guard. Because it's so massive, it would attract, with the force of gravity, it would attract a lot of the comets, asteroids, meteorites, before they came down to the Earth. But 65 million years ago, he let down his guard and let it whopper through. Got through the Earth's atmosphere as well. An asteroid. Some even say it might have been a comet, but pretty well everyone thinks it's an asteroid. Hit the Yucatan Peninsula. Caused quite a commotion. All that impact forced a lot of heat, burnt off a lot of the vegetation, and spewed up a great deal of material from the Earth into the atmosphere. And that started to go around the Earth, circle the Earth, cut off the sunlight. And dinosaurs, which needed that, and also eat large amounts of vegetation, died off. That allowed the mammals to come out into the daylight and proliferate. They took over a lot of niches that formerly were occupied by the dinosaurs. So, although you can say it's a catastrophe, it's good for you, well, not so good for the dinosaurs. So you made it through that period of time. Now, 10 million years ago, the continent of North America and South America came together. Before that, they were actually separate. And that changed the ocean current, the ocean currents, and the climate of Africa. So Africa, before that, was a lot of trees, and now they can no longer support the number of trees and had a lot of grassland or savanna. So some of the animals up in the trees, they said, I'll give that a try. It's pretty crowded up here. And so they went down, tried their luck on the grasslands, and as luck would have it, probably from a cosmic ray, came down and modified their DNA. And those animals that had a better opportunity of surviving in the grassland went on and gave them that modified DNA to their offspring. And as I say, that's the process called mutation. Now, of course, there'd be lots of mutations that didn't work. Maybe they came up with two heads, two brains. Well, is two brains better than one? Well, we should ask an octopus, because they have 9 brains. They have one in each arm and one in each, and one central. So it may be not as bad as you might think, although humans pretty well only end up with one head. So, again, there's a lot of steps that happen for you to be here. Your mother and father had to meet, and they had to produce you. You get half of your DNA from them. And their father and mother had to meet and pass on their DNA. So you are a quarter, your physical characteristics is composed of a quarter of your grandfather and your grandmother. 4. All right? I think so. Yeah. And then over the next 100 years, 3-4 generations, will be 16 different. Seems like it should be more, but okay, in the million years, that would have been 16,000. So you're part of 16,000 different people, physically. And then you're on a planet, one of 7 now, I think, and the planet supports complex life like you. It's not too far from the sun, otherwise water would freeze, and most people think the water is essential for life. Or not too close, so the water would evaporate. They were in the Goldilocks position. Now, science is now trying to look for other planets around other stars, and now they realize that there are planets. Pretty well, most of the stars they looked at, they see there are planets. Some more than one or two. So they're looking for that Goldilocks position, and maybe looking if the atmosphere has water or oxygen to indicate that there's life on that. So far, they have not found it, but they see several candidates. And they also looked in the solar system. There are many more dwarf planets, probably more dwarf planets in the solar system than there are planets. We just demoted Pluto to a dwarf planet. And there's water on Pluto and on its moons. It's frozen, but underneath the frozen water would be liquid water. And there might be microbiological entities in that water. So it's possible that we may even find life in the solar system. And looking at Mars, for instance, we see canals. So there must have been water in it at one time. The atmosphere is not conducive, but then since the Mars is smaller, the center of it would have solidified, and it wouldn't be molten iron like there is on the Earth, and therefore the atmosphere wouldn't have a larger electromagnetic shield to keep the atmosphere in place. And also the force of gravity wouldn't be as great, so that it wouldn't have as much attraction to the molecules in space. And one of the great scientists that was helped search for life, search for extraterrestrial, intelligence, SETI, Carl Sagan. He came up with, he produced a series called Cosmos, which explained a lot of what goes on in the universe. For instance, he said that you were stardust. Not to quibble, but the majority of our atoms are really not stardust. The rest of your atoms are. And he also said the expression, the pale blue dot, referring to the Earth. When you see it in space, surrounded by darkness, is a small blue dot, blue because it's got water, where everything that we know about has happened. Every single thought, every single event that the humans have experienced, at least, happened to that one little small dot, which he likened to an organism. And when one part of the organism doesn't work that well, then the whole organism is at risk. And so that's one way of thinking of the Earth. Now, Neil deGrasse Tyson has gone on, and he was inspired by Carl Sagan, and he's now narrating another series of Cosmos, which explains a lot of different scientific facts. And it's a series of over 12 or so. But as I say, life, complex life as we know it, just seems to be so far here. And then the Earth is part of the solar system, and the solar system is part of a galaxy which has 100 billion to 200 billion stars. And that galaxy is part of something else which has the universe, which has 100 billion to 200 billion galaxies. And you got everything but your hydrogen over that period of time, 13.8 billion. And it does say plus, it should have said minus 308,000 years ago. So one of your carbon atoms in your finger could be 12 billion years old. A carbon atom in another finger could be 6 billion years old. So all those different steps, all those different things had to come together. One planet in 7, one solar system in 100 billion, one galaxy in 100, 200 billion, for you to be here. So a lot of different events. And then, of course, at 380,000 years after the Big Bang, then you've got all 50% of your other atoms, your hydrogen. Then in 1 second, you got all your particles, because if they just had particles and antiparticles, then you wouldn't exist. With the rest of the universe. So you had 1 billion to 1 chance of getting through that. And then, of course, at within the 1 second, you got your force of gravity, keeps you grounded, and the electromagnetic force, which keeps you from falling through into the Earth, and the weak force, which protects you from all the radiation from the sun, and the cosmic radiation, and protects the atmosphere, which gives you your oxygen and protects you from things from falling down, a lot of them from falling down and hitting you. And your strong force, which keeps you together. Otherwise you fall apart. And then, of course, the universe. How did that happen? Don't know. Are there other universes? Some speculate that there may be, but there's no empirical proof of that. So, really, quite miraculous that you made it through all those, and many of which science cannot explain. Now, some of the other physical attributes, your weight. Now, before the 1600s, nobody really understood how you got your weight. But Newton, back at the 1600s, he saw an apple fall to the ground in the orchard outside of his house. And he speculated, well, that's because there's a force of attraction between that apple and the center and the earth. And he went on to produce a formula, mathematical formula. He said it's proportional, if you like, equal to the mass, the amount of material in the apple, and the mass times the mass of the earth, the amount of material in the earth, divided by the center, by the distance between your center of gravity, or the center of gravity of the apple, rather, and the center of gravity of the earth, squared, multiplied by itself. And what is that? Well, that's gravity. So, when I said that you maybe weren't, were mostly space, and it's 99.9999999% space, more than what I said before, and you're nothing at all, maybe no one notices you or hears you, well, you are attractive. you could say, well, no, I maybe don't look too bad if I'm far away, but when you get closer and look up close, you'll see that I have lots of flaws. I'm overweight, I'm too fat. But don't. The closer you are to someone else and the bigger you are, the more attractive you are. And that attractiveness is equal to your mass times the mass of the other person divided by the square of the distance between you two. Now you don't really notice it because it's not all that much. You're not all that attractive. But you're more attractive when it comes to going outside to a mountain, or the mountain to you. And you're more attracted to the earth, quite attracted to the earth, and the earth to you. To measure that attraction, you slide something in between you and the earth. We call it a tool, we call it a scale. And what is that? That's your weight. So your weight is the attraction between you and the earth, and the formula which I just went over. But I think I might have misled you again. You don't attracted to that person. You fall for them. They have created a space around them, and you fall into that space. So space is not constant. Here's where I get somewhat sexist. Because every female that has always fell for every other male that ever existed, that they ever met, and will fall for every male that they will ever meet in the future. Do we call them fallen women? Well, we don't call men fall for all women and fallen men. So I guess it is sexist. But to be fair, men also fall for other men. What happens is the mass of the other person creates changes the space around them, and you fall into that space. Like if you're on a trampoline, for instance, form a indentation in the trampoline, so you can think of the trampoline as space. And you put a basketball on it, and the basketball rolls towards you, falls towards you, and the closer it gets, the harder it falls. So Einstein, being quite clever, said that gravity is not attraction between two objects like Newton said. It's a warp in space-time. Space and time are quite closely interrelated. He came up with that idea with a thought experiment. Here's another thought experiment. You take two ball bearings, place them on a stretched out rubber sheet. Well, you first have the rubber sheet representing space-time, and the large ball bearing, say, representing the Earth, and the small ball bearing representing the Moon. And you place the large ball bearing on the rubber sheet, in other words, the Earth in space-time, and it causes an indentation, or in the case of the Earth, it causes a warp around the Earth. The space changes. And you roll the smaller ball bearing, representing the Moon, towards the larger ball bearing, representing the Earth. And then, depending on how fast you roll it, how massive the two objects are, how close the smaller ball bearing comes to the larger, it'll either go right by, or hit the indentation, or in the case of the warp, and be deflected. Or it'll go and hit the indentation in the case of the ball bearing, or the warp in the case of the Earth, and go around it, circle around it. So it's not an attraction between the moon and the Earth. It's a warp in space-time. The mass of the Earth has changed the space around the Earth, and this moon has fallen into it. Now, why does the moon keep going? Why doesn't it stop? I mean, before Newton, Archimedes, Aristotle, said that the natural thing would be for something to stop. Newton says, no, everything's got to keep going unless something stops it. A law of momentum. Aristotle said, no, you get things moving, you'd have to have a prime mover, like God, and you'd have to keep it moving, you have to have the arm of God. Newton says, no, using his two laws. Take an thought experiment. Take a cannonball and a cannon up onto a mountain. Drop the cannonball down, and it drops to the top of the mountain, just like the apple below falls to the earth. But shoot the cannonball out, and it keeps going. It may go a kilometer or a mile or a kilometer before it drops. If you shoot it hard, it'll go halfway around the world, halfway around the earth. Harder again, it'll go all the way around before it drops. Harder again, it'll go around and keep going. The law of motion and so it's the gravity then, and the fact that something keeps going, the centrifugal force, if you like, that the moon goes around the Earth, and the Earth goes around the sun. Whereas Einstein says, no, it's a warp in space-time. Now, many of the people, the consensus of scientists, said, well, no, that doesn't make any sense. What are they talking about? Warp in space-time, what's that? And some of the journalists at least said, listen, there's a consensus of opinion that your idea is false. And Einstein, being quite sure, he says, well, all I need is one scientist or one person with one piece of evidence that does not comply with this theory and or this hypothesis, and then you can say it's wrong. In other words, you need evidence, not opinions. And all you need is one piece of evidence that doesn't comply. So when, and perhaps it's right to be skeptical, because that's how science works, really. And people propose a hypothesis, and then other people have to prove it. And it could be right, could be wrong. So it could be a mistake, it could be correct. And that's how science does progress. And sometimes, of course, they make colossal mistakes before they admit that they're wrong. And when, and this is the second theory, or the general theory of relativity, so when someone got the evidence and how they did that, took it back into the lab to the hypothesis, and used a piece of equipment called the solar system. And the solar system, the sun, when it goes into a solar eclipse, you look at the photons, the light that goes past the sun, and they found that the photons were deflected. In other words, the stars appeared in a different location. Photons which don't have mass was deflected by the warp caused by the sun. And then Einstein became very famous. So is Newton wrong and Einstein right? Yes and no. Because we still use Newton's laws for a lot of practical reasons, being less complex than Einstein's. For instance, to land a man on the moon or to send rockets off farther, that they go out of their own steam by using the force of gravity of the other planets. So we can say that Newton is right as long as we restrict it, because it doesn't do some things 100%. It doesn't explain how Mercury goes around the Earth. Sorry, Mercury goes around the Sun. Because Mercury being closer to the Sun is more affected by the warp caused by the mass of the Sun, and you have to use Einstein's equations to more definitively look at how Mercury goes around the Sun. The other thing I didn't mention before is Einstein says it's a warp in space-time. So time changes too. You think it's crazy enough to say that space changes, but also time changes when you approach a mass, come into the warp of a mass. And the closer you are, the slower time goes. So again, does that really matter? Everyday use? Because we're pretty well all at the same distance from this, in the same position in the warp that's caused by the Earth. So our time really runs pretty well the same for everybody. But what if you're on a satellite? You're out farther on the warp. And the time on the satellite, it runs faster. Actually runs faster than the time on the Earth. You need an atomic clock to measure it. But suppose you want to use your GPS to go someplace. Well, if you don't incorporate Einstein's general theory of relativity, your GPS would be out in 2 hours and you would be lost. So there's two places where you can't use Newton's laws. You have to use Einstein. So an example, then this is an example where a new piece of evidence comes along, or a new theory, and you can still use the old one as long as you restrict it and make sure you use it only where it works under certain conditions. Now, this is really then a worldview of how the universe works, or how everything works. Crazy as it may be, that's how science explains everything in how the world works. Did Einstein get a Nobel Prize for that? No. He got a Nobel Prize, but for his contribution to another theory of the how the world works, the quantum world. He contributed to the photoelectric effect, where if you hit an atom with light, then it gives off electrons. So you can thank Einstein. When you go through an elevator door and it starts to close, it opens again. Or when the garage door starts to close and then the car opens again and doesn't hit the car. And Einstein didn't like the other world vision. Because it uses probabilities. One of the founders, of course, is Planck, where he said that everything is not continuous as it would be in Einstein's world. You break it down, you get to the smallest quanta of time and quanta of length or space. Another would be Heisenberg, who says you can't be certain, really, about any two things that are related. The more certain you are of one, the less certain you'll be of the other. Principle of uncertainty. For instance, if you want to find the speed of a particle, and you want to find its location, the more determined you are, the more you know about the speed, the less you know about the position, and vice versa. Not because there's a problem with measurement, but that's reality at the quantum world. And as I say, they use probabilities. So it's only when you add up all those probabilities that we get anything approaching what we think as in the rough reality. But in the quantum world, everything is probabilistic. It's to show the weirdness. The classic experiment is a double slit experiment, where you pass light through two slits to see what happens on the other side, let's say the wall on the other side. Now you think, well, maybe you just get the two lights, two lines of light. No. You get several lines. Because light can be both a wave and a particle, which is weird. And what those several lines are are interference lines. I think I mentioned before, but if you hold up your two fingers together and look through with one eye, you'll see some faint lines in between them. And those are called interference lines, where the waves interfere with each other, just like when you throw two rocks into a pool, then the waves will interfere with each other. So when you pass that light through those two slits, you get several lines, interference lines. But guess what? If you observe the light or measure the light, try to measure the light before it goes through, then you only get two lines, indicating it must be a particle then. So somehow the wave is changed back into a particle. Very weird. And not only that, if you release one photon at a time, then for sure it would have to go either through the left or the right, and therefore over time would build up one or the other line. No, it has several lines, indicating the photon must have interfered with itself, or must have gone through the two slits at the same time. And even again, if you observe each photon as it goes through, before it goes through, then you get two lines indicating, well, no, it's just as it should be. The particle either goes to the left or right. And one of the other founders who made contribution to how you can work out things in quantum mechanics. The name escapes me right now, but he said anyone that thinks they understand quantum mechanics doesn't understand quantum mechanics. And yet, you can call it a theory because all the evidence so far supports it. You can work out things more accurately than any other tool in science. 23 decimal places, for instance. And there's no evidence that you have that contradicts the quantum mechanics. And now they're saying quantum field theory, everything is a wave before it changes into a particle. So you have two different theories of how the world works, and you call them theories because there's no evidence to prove them. They're not correct. And yet they're totally incompatible. So here is a quandary, if you like. Science really doesn't know on the fundamental level how the universe works, how everything works. And yet the evidence seems to support, always does, supports one or the other. And you can get away with it Somewhat, because in the quantum mechanics, everything is very small, and the mass would be small, and the force of gravity is small. So you can pretty well ignore gravity, whereas you can't in the Einsteinian world. Except when you have something small and massive, like in a black hole, or like the beginning of the universe. And science is trying to find a theory that combines the two. So a theory of everything, or quantum gravity. And as I say, Einstein didn't like the other theory. He thought he could have a theory of quantum gravity. It doesn't rely on probabilities. He said God does not play dice. And he also said that if once you have combine the two theories and find a theory of everything, then perhaps then you would better know the mind of God. Yes, in the Einsteinian world, time is not constant. And there's some, if you want weird things that you don't think of. For instance, you're in that room and you ask somebody how they are. Well, you want to know how they are at that particular time. But no. You can find out how they were billions and trillions of Planck times ago. Because since light is constant, 10 to the 10 centimeters per second, it takes light some time before it reaches you from them. So you never know really how they are at that particular time. And when you look at the moon, you're only seeing as it was 1.2 seconds ago. Because it takes light that long for it to reach you. And when you look at the sun, it's 8 or 9 minutes for this light to come towards you. Because it takes that long for it to reach you. Now, when we get to distances bigger, longer than that, we use the time that light travels to get you as the measure of distance. So we'd say that the moon is 1.2 light seconds away as a distance. And the sun is 8 to 9 light minutes. Now, do you believe in ghosts then? Or do you believe in time travel? Well, all you have to do then to find a ghost is to go out and look into the sky. Because many of those stars that you see are dead. And you're only seeing the light that's come from them. Because they could be a light year away, they could be thousands of light years away, and they could be 1,000,000 light years away. The farthest star is look through the Hubble telescope, is 13 billion light years away. Because it takes light that long for it to come. So you occupy a space then in this world, a very minuscule space between one Planck length, 1.6 times 10 to the minus 35 meters, and 13 billion, 13.8 actually billion light years. Quite an insignificant space, really, in the totality of things. Now, about time, you want to see. Therefore, you're seeing in the past. When you look in the sky, you see how it was before. When you see a star, you're traveling back in at least observing what has happened in the past. You ought to time travel then and see what's happening in the future. Well, you can do that too, because also know that the faster you go, the slower time goes. So it's not only mass that affects the time, it's the speed too. Here's a thought experiment to see if you don't believe that. You have a friend and he wants to go on a trip, so you stay behind and you say, well listen, go on a train, and when the train gets 100 miles an hour, go up to the front and throw a baseball 100 miles an hour. I want to see how fast it goes. Well, it goes, ignoring French, 200 miles per hour. Then he says, well, wait till the train goes 3/4 the speed of light and go up and throw it at 3/4 the speed of light and see how fast it goes. It can't go 1.5 times the speed of light, because the speed of light is constant. It just goes the speed of light. It can't go faster. Something's got to give. Distance you go is equal to your velocity times your time, or how fast you go and how long you go. So time can't go faster than the speed of light. The velocity, sorry, can't go faster than the speed of light. So time has to change. And it does by slowing down the faster you go. So you want to see into the future, get into a rocket ship and travel near the speed of light, or near the speed of light. You can't go faster. And depending on how long you go, how fast you go, when you come back, everything else would have aged. You see what the future will look like. So really, you're seeing into the future. So as I say, both the Einsteinian and the quantum mechanics really are quite weird. And they are incompatible. And science cannot explain a lot of the different events that got you here. But one of the things that can explain is why all of the forces and all of the constants to explain everything, why are they exactly the way they are? Because if some of them were different, again, you wouldn't be here. For instance, force of gravity, if it were any less, then it wouldn't have been able to concentrate all the hydrogen into stars and eventually the rest of the universe. The universe would just be all hydrogen. And if it was any stronger, after the hydrogen was created, it would have been force of gravity would have brought it back together into a big crunch, so to speak. So how come that force is exactly the way it has to be? Because if it were any different by a minute amount, we wouldn't be. We would be. The other one, which is even more diabolical, is the cosmological constant, which Einstein put into his general theory of relativity and then took it out. It would allow the universe to expand or contract. He took it out because he, like everybody else, thought, oh no, the universe is the way it is. It's always been that way and always will be. He called it the biggest mistake in his career, and the biggest mistake was thinking that it was a mistake to put it in. Because it's now needed to explain the expansion of the universe. So the scientists said, well, let's look and see just exactly how much it's going to expand, when it's going to slow down, cool down, stop, maybe go back into a big crunch with the force of gravity. And to their surprise, they found it wasn't slowing down. It was accelerating. So it must be something counteracting gravity, because gravity attracts everything together, and this energy then is something that forces everything apart. They didn't know what it is, so they call it dark energy. And in order to explain what is happening, it needs to be 70% of the universe. Now they speculate or hypothesize that space is not empty. It's full of virtual particles and virtual antiparticles. Hard to measure them, by the way, because they're virtual. So this is just a theory, or just a theoretical, or just a hypothesis. And when they come together, they annihilate each other and get energy. That's where you get your dark energy from, if you want to call it vacuum energy. And as the universe expands, then space expands. There's more space, therefore more virtual particles and antiparticles, and more dark energy. So dark energy is winning over gravity. Starting even 9 billion years ago, it's outweighing gravity. So it'll keep on expanding, and maybe you won't be able to see stars in the future because they'll be too far away to see. So here's another thing that science has not got an answer for. Okay. And when they looked at the dark energy, the lampa, in Einstein's general theory of relativity, they were even more shocked, because the what they came up with was out by what actually happens by 10 to the 120th. Largest discrepancy ever. So maybe science doesn't really have a grip on everything, because it's out, if it's out by that much. So maybe there's some underlying principle, as Einstein would say, that can combine and have a theory of everything. Now they also found out that there was not enough gravity, not enough mass in the universe. How'd they find that out? Well, when a skater spins, when they put their arms out, they go slower. When they bring their arms in, they go faster. So the closer you are to the mass, the faster you go. And like in the solar system, Pluto goes around the sun much slower than Mercury. And what they found is that this rule, if you like, applies, but it doesn't apply when you get a solar system or a star going around the center of the universe, center of the galaxy, sorry, which is a black hole, most likely. Most galaxies have a big black hole in the center that attracts all the stars. But in this case, it doesn't work out. They need more gravity. You need 4 or 5 times as much gravity to explain that. and also to explain how at the beginning of the universe, gravity brought together all of the hydrogen. So you're only left with 5%. Science is in the dark 95% of the time of the universe. And that 5%, it has two conflicting views or theories. Call them a theory because they have evidence to support both. So when science says, well, we know everything, well, they don't. And so there's definitely room for a more spiritual or religious contemplations. Now, the other thing that science cannot explain is why do you get all these, derive all these formulas and laws and theories? How do you eke them out of the universe? For instance, before, and a lot of them have been modified or changed, so you can't always say that it's because it's a scientific fact that it's correct, because it could change. For instance, like there were all sorts of laws before 1905. People thought there was a conservation of energy, conservation of matter. That energy and matter or mass were different. Einstein said no. His special law of relativity said no, they're equal. E equal mc squared. And they also had Newton had his laws describing gravity, attraction between two objects, divided by their product, divided by the square of the distance between them, and law of conservation of motion. And he treated time and space as being constant. And then after 1905, he said, no, energy and matter are the same, E equal mc squared. And time and space change. And gravity is not a force of attraction between two objects, but a warp in space-time. And we get all the laws of quantum mechanics, which are more accurate than anything else. And yet we don't really understand the underlying principle. So what if it's the other way around? The universe or reality is created from these equations or from the mind. We do create virtual reality. You have performers that have died before on stage, performing their music or whatever. They're holograms, so they don't exist, but they're virtual. And the idea is, what do I do? Do I clap when they stop? Because they're really not there. They're only holograms. Now, to be truthful, you'd have to have something a lot more smarter, omniscient, say, more powerful, say, omnipotence, and happening everywhere, say, omnipresence, before you could create the whole universe. Well, these are exactly things that people say that God is. And it's got an infinite mind, so science cannot, and never will, be able to say what happens at time equals zero. Because according to science, it can't be less than one Planck time. So you could equally say that there's something infinite that creates the finite. And science is in no position really to say anything different. So, we often say, if we can't understand something, or and think we never will. God only knows why that happens or that doesn't happen. And when something happens, fortuitous, or doesn't happen, it was harmful, we say, thank God that happened, or thank God that didn't happen. Otherwise, we'd be in trouble. For instance, thank God that you have the force of gravity. Otherwise, you wouldn't stay grounded. You'd fly off. Thank God there's an electromagnetic force stronger than the force of gravity. It keeps you from falling right through down to the center of the earth, which could be, say, a black hole or singularity. And God only knows what that is. Thank God there's a strong force that keeps you from flying apart. Thank God there's the weak force that keeps you protected from the solar and cosmic radiation and being hit by asteroids. And thank God the other trillion and billion of things that occurred, all the different steps happened, otherwise you wouldn't be here. So whether you take it literally, and do thank God, God that is everywhere, like you say, took everywhere to change you. Waves in the matter, the science says, observing. Or whether you think it's just accidents, random accidents, fortuitous as they may be, that you arrived here, is nevertheless miraculous, considering all the things you had to go through to get here. So you are a miracle, whether you think you are or not. So basically, you could say then that maybe science needs the religion to come up with these. You can also say, as we will say in Science and Religion 5, that maybe science needs a moral compass. Because science is so powerful now, it can do things that maybe are deleterious. Just because it allows you to do something doesn't mean that necessarily you should. Even when you get to the fact that the mass is converted into energy, well, that's the hydrogen bomb. And is that good? And genetically modified. We now know so much that we can genetically modify. And the telecommunication is so powerful now, we can monitor almost everything that people do. So I'll talk further to that, and Science and Religion 5. It's enough for now. Thank you.